Hello guys, welcome back. This is our third and last video on chapter 2 problems. This time we have problem 255 in which we are being told that we have a 75 horsepower motor. This 75 horsepower is the shaft output and has an efficiency of 91%. This motor is worn out and is replaced by a high efficiency motor of the same output but 95.4% efficiency. So what is the reduction of heat gain at the room to higher efficiency under full load conditions? So we could have here our old motor, and we know that this motor delivers 75 horsepower and efficiency is 91%. So if we remember our first law definition, we know that this efficiency is the work divided by the heat. So we can solve for heat, and we can see that this will be the work divided by efficiency. If we substitute our data, we have 75 horsepower, but we would like to have everything in international systems, so we know that 0.7046 kilowatts is 1 horsepower, so this cancel, and efficiency is 0.91. So this Q inlet in the old motor is 61.483 kilowatts. That's the old. Now for the new, we have the same 75 of power, but now the efficiency is 0.95. So repeating the same procedure, we can get that the heat inlet will be 58.894 kilowatts, and I would like to ask that you can solve this yourselves. Just check that we have the right number. You know that I can make mistakes at class. So the heat reduction will be Q that we have in the old one minus the Q that we have in the new one, because we are releasing heat anyway. So that will be the reduction. So that difference is 2.589 kilowatts. And again, please just check the answer. Thank you. Hello guys, this is the last problem we are solving. We have an oil pump that is moved by an electric motor that draws 35 kilowatts of power, and is pumping oil with a certain density. We know that the rate of pumping rate is 0.1 cubic meter per second, and we're given that the inlet outlet will have different cross sections that will affect the velocity. Since the volume is constant, the volumetric flow rate is constant, this should change our velocity. Okay, and we know that the pressure increase that we have is 400 kilopascal, and the motor efficiency is 90%. So first of all, we are asked to compute the shaft, the motor efficiency of this pump, the mechanical efficiency of the pump. Okay, so if we would like to get that motor efficiency, that pump efficiency, we know that it will be what we want, which is the useful power that we're imposing to the fluid divided by the shaft work that we are introducing. But we are not giving the shaft work, we are giving the electric work. But we know that we can't get the motor efficiency can be computed as what we want, which is the shaft work, the shaft power, divided by the electric power that we are giving. So since we know the efficiency of the motor, we can get the shaft power as the efficiency of the motor times the electric power that we are supplying. So this will be 0.9 times 35 kilowatts. This will be 31.5 kilowatts. This is the shaft work, shaft power. What this means is that in the shaft we are having 31.5 here, and the remaining 3.5 kilowatts are just transfer as heat. It's part of the inefficiencies. Okay, so what we are next, we need to compute this useful work. What is the work that we are giving to the fluid? Since we can anticipate that we have a change of velocity because of change of areas, we can compute that velocity. If we remember that the volumetric flow rate is equal to the velocity times the area. Since this is constant, we can compute that each velocity will be the volumetric flow rate divided by area. In other words, will be the volumetric flow rate times pi diameter squared over 4. So this is 4 times the volumetric divided by p pi diameter over 4. Using this expression, we can get that velocity 1 is 19.84 meters per second, and velocity 2 will be 8.84 meters per second. Again, check these numbers. That means do it. Okay, so we have this velocity, and we know that this useful work, since we don't have any heat going in or out from the pump, we don't have any work out, all we have is work in. this work in will be the volumetric flow rate times delta P plus the change in kinetic energy. So that would be my flow rate times my density times this, of course, is a mass flow rate. Change in kinetic energy, P2 square minus V1 square over 2. If we substitute these numbers, we will see that this is 26.40 kilowatts, and again you just need to substitute these numbers, so check the numbers again. Finally, the efficiency of the pump will be the useful work, the work that my fluid is receiving, which is 26.4 kilowatts, by the shaft work, the work that the pump is receiving, which we said was 31.5 kilowatts. Efficiency is an n-dimensional number, and this gives us 0.838. If we apply in percent, we know that is 83.8%. What does this mean is that out of the change like this, we receive, this in blue, we receive 35 kilowatts from the company. We lose, we pass 31.5, and we lose, let me change this so we don't have, this is the way we are doing. We have 35 kilowatts of electricity. Out of those, 31, this is electricity. 31.5 are in the shaft, while 3.5 are lost at heat. Out of this 31.5, we only pass 26.4 to the fluid, and the difference, which will be for 1.1, is lost in friction. Okay, with this we finish our second chapter exercises. I hope that they help. Thank you.